we talk about three methods at a time, together, so-called Chord, Secant, and Newton's method. All right, Newton's method. The idea is that, remember, for the bisection, we'll only look at the signs, right? Only look at signs. You take 2 points, you evaluate the signs, and if it has opposite signs, then there's zero, and you use that information to keep shrinking, right, to which half. The idea is we should use more information, right? Use more information than just the sign, right, of the function f, right, of the function f. This whole function is there, f of x. You put any x in, you can evaluate. Don't just look at the sign, right? As a typical lesson as well. Use all the information you have. Think of something that you have not used that might be helpful, right? For example, it can be f at your xk, maybe f prime xk, right? Could be anything that might be helpful for you, right? All right, so what I'm going to do first, is I'm going to review the so-called Taylor series. Taylor series, all right? Taylor expansion. Okay. How many of you remember Taylor expansion? All right. See a couple of hands. That's not a great sign, right? I've already told students in this class, the only 2 things you need, right, for this class, to succeed in the class, is Taylor expansion and being careful. They can do this. This is numerical analysis 1. Right? So this is about approximating. This couple of classes of material from calculus. I'm not going to do them in a lot of details, but I'm going to summarize some of the things for you here, right? Approximating a function f of x around some fixed point x. Fixed point x. Think of it that way. All right. So you have a function f of x at some point x. All right, at some point x, and x is fixed given any point, given any fixed point. Right? You're trying to look at a neighborhood. A neighborhood, NBHD, a neighborhood of x. All right, neighborhood. And ask yourself, this f of x might be very complicated. Might be, it's not the Euro functions that you see, not polynomial, maybe not even trigonometric functions, not exponential. How can you best approximate it? By simple functions. In this case, by polynomials, actually. Right? By polynomials. So if the interval is really tiny, the neighborhood is tiny, right? It's like you take a magnifier and look at the function. There's one tiny bit of the function, right? What do you see? Just take one tiny piece. You see a straight line, right? Pretty much a straight line, So I'm going to introduce maybe slightly different notation than you saw for those those who remember. For the idea of the neighborhood of x is a little neighborhood, right? That's what we care. We're going to use this as analysis. We always consider some neighborhood of some points, right? That we want to solve whatever we want to solve, and because of that concept, we're going to introduce x plus h. X plus h. H is small, right? H is small. H is small and changing. It's a variable. So that way, x is fixed, but x plus h would cover a neighborhood, right? H is 0 all the way to 0.01, for example, or can be negative. Then it goes to the left, right? So I'm reviewing this, and this is probably the only time to review this, right? This is a prerequisite for the class. I'm reviewing this for your benefit. So h can go from anywhere between negative 0.01 to positive 0.01. Then by varying the h is a variable. By varying the h, you are going to cover this little neighborhood. Is that clear? Is that concept clear? It's very important, right? We read two letters, x, but x is fixed, h is changing. Consider h as a variable, something that varies. Right? So by approximating, we meant that we can actually write down something for x plus h. Is any point in the neighborhood. Any point in the neighborhood. So any point in this neighborhood, x plus h. All right. We are going to use the series is then a series of more and more accurate approximation to the function. All right, to the function. If you were to use a constant, so for polynomial, that means we're using higher and higher degree polynomials to approximate the function. The lowest degree polynomial is degree 0, which is a constant. If you were to use a constant to approximate this guy, what would you use? F of So if you were to use a constant, you should use f of x, because at least that's accurate for x, right? One obvious intuition, right? So it's accurate for x. It should be accurate when you move tiny bit away from x, right? We keep going to make it more and more accurate, basically, all right? The second is you're going to use a degree 1, which is straight line, right? Which is a straight line. A straight line, we need for it's a what's that? Point slope form, right? Point slope form. We need a slope. If we were to use a straight line to approximate this tiny segment, what's the slope you should use? 1. So the slope should be the derivative at x, which is a tangent line, right? Times what? Times h. H is a run, right? Run from x to x plus h. You're approximating x plus h. You go from x to x plus h. The difference is h. Right? and plus you go to second term, which would be h squared. H is a variable, remember, h is a variable. So it's h to the 0, h to the 1, h to the squared, h cubed, and so on and so forth. All right? And that turns out to be f double prime x over, anybody remembers? 2 h squared plus dot 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 all the way to, if we want h to the nth degree polynomial, you can keep raising the polynomial degree. For the nth degree polynomial is f to the nth derivative evaluate at x. X is a fixed point, so evaluate it divided by, yes, m factorial, exactly, m factorial. And you keep going. Keep going. Okay. So again, so here we are matching more and more terms. We match the point value, match the derivative, second derivative, and so on and so forth, all the way to the nth derivative, right? If you keep n terms and a to the n plus 1 terms, there is constant term, right? Another way of write this is that, of course, this can be written as if you are approximating x, right, and you approximate around alpha, right? So x around alpha. Now x is changing, alpha is fixed. The moment we say x around alpha, we expand the function of f of x around alpha. That means alpha is like our previous x. The x is like our previous x plus h. X plus h. H is a step size, right? X plus h. X plus h was in the neighborhood of x. Now x is in the neighborhood of alpha. Right? So this is f prime alpha times what? What's our new h? Not x anymore, right? Because if it were x, then it would have been x plus h above, but it was not x plus h. It's the step size, the run. What's the run here from alpha to x? X minus alpha. No? X minus alpha. So the next is f. It's too crowded. So the next is f double prime alpha times x minus alpha squared over 2. Right, you can put it to anywhere, it doesn't really matter. All right, and you keep going. Suppose I stop here, right? Stop here. I don't want to write dot 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 and the series keep going. I just want to another term to make it equality. I don't like summation. I just want one simple term. The summation is like in series. It goes to infinity, right? I mean that's a good reminder. I should have done it, but that's all these series can be written in terms of summation, of course. If I want to stop here, right? I want to stop here. This is f. The next guy is triple prime, right? If we want to keep going, I'm going to write my contribution, right? Here is going to be x minus alpha cubed over 3 factorial, right? If I put alpha there, there's just one more term, then we'll have to keep going. It's an infinite series. What I'm asking here is that if I want to stop here and make it equality, I don't keep writing. I don't try dot, dot, or summation sign. Then what should I do? Yes?
What applications are there for this?
Let me write an even simpler form. If I have fx, f alpha, and I just want to include one more term. I just want to stop there. What do we do? If you still don't recognize, I'm going to plot a picture for you. Again, we're going to use these things like in a split of a second later. All right? So you better make sure you understand this. These are all from calculus. If I have, here's my base alpha, here's my changing point x. All right? I have a function, right, from, I mean, here f of alpha is equal to 0. That doesn't matter. You can leave it. Or, so what I'm asking is that, what should I put it here so that if I rewrite the last term, the last equality, that is f of x minus f of alpha divided by x minus alpha. Right? So this guy is the same as that guy. You see that? I'm just rewriting it. I move f of alpha to the left and divide both sides by x minus alpha. And here is my f alpha, here is my f of x. So what is the right-hand side of this term, this equality? Fx minus f alpha divided by x minus alpha. What is it? It's the what of the red line? A slope, right, slope. Can you then visualize that I'm going to take this line segment, the slope of this guy. I'm going to take this guy. Listen, right? I think this is the most intuitive explanation of this. I hope by the end of the day, you'll never forget about this. I'm going to take this line. I'm going to move it so it will touch only one point with my curve. You realize that? We don't need to write an algorithm to do it, or we could, but that's not the point. We can do a little animation. So we can shift this red line to here. So it is tangent to the curve. It is only touches the curve with 1 point. Can you visualize that? You're shifting the line, you're shifting the red line. That means you are not changing the slope. The point that it touches with the curve, if I'm going to use Kasi to denote that point, another fancy letter mathematicians like, it's a Greek letter Kasi. All right, Kasi. I'm going to use Kasi to denote that intersection point, that tangent point. So what's the slope in terms of Kasi? This answer Michelle just gave for the last question, right? The slope of this line, of the purple line, is equal to the slope of the red line. On one hand, the slope is equal to this quotient. On the other hand, the slope is equal to something in terms of Kasi. What is it? Marco, what is it?
Whatever you want to write. Wait, in terms of Cosine?
Yeah.
In terms of x and alpha?
In terms of Kasi. In terms of x alpha, we already have it, right? That's on one hand, we have the in terms of x alpha. I don't want it that anymore. To make an equality, You want two sides. On one side is this guy, on the other side is something else. Then we have equality. So what is it in terms of c and f? Yes. The derivative again, exactly. The derivative. The quotient is a derivative. The quotient is a slope. The derivative is a slope. They are two different ways of representing the slope of the same line. So they must be equal. Right? They must be equal. So the c should be here. Because those two are the slope of the same line. Which means we should put c there. For some c, so to finish this, for c between x and alpha, right? For c between x and alpha, you just don't know where c is, because for one function, c might be the middle point. For the other function, c might be the 0.7, 0.3 split, whatever. Yeah. So it's c here as well. For c between x and alpha. All right, x and alpha. Okay. Is that clear? If you completely forgot about Taylor series, of course this is going to be hard, and it takes 17 times reviewing, right? Not one less. And if you don't do that, next class you have no idea what we're doing here, because we're going to use that just like that. So, in particular, what we're going back to what we were talking about, right? Going back to what we were talking about, we're trying to approximate the zeros of nonlinear functions. Later on, nonlinear systems. Or systems, linear systems. All right. We'll have x0, x1, and so on and so forth. Remember, if we're going to approximate the next guy, we have xk, the current, k0. Currently we are at x0. When k is 17, we know x17. We need to get to x18, right? The 18th bisection. The next guess, keep iterating. The next iterate is x k plus 1, right? X k plus 1. We use what we just did, reviewed, all right? If we x k plus 1 is most of the time fairly close to xk, you're not going to change your last guess a lot. Okay? So we're going to expand the function around xk. Now that becomes very important, right? When we say expand, what function around where? Because if the base is different, the formula will be different. Here we are expanding this around xk. Around xk, the current iterate, the current guess. This would be fxk plus we use this guy. We use this guy, right? We use this guy. So we're going to take. You're going to plug in xk plus 1 for x, plug in xk for alpha. That's easy. So this is f prime at some c times xk plus 1 minus xk. Right? xk. All right? You see that? That's again the same picture, right? We'll go from xk to xk plus 1. Okay? We'll use the exact formula. For c between xk and xk plus 1. Xk plus 1. All right? And the next is we need to keep in mind our goal. The goal, the goal is to solve f of x equal to 0, right? Solve f of x equal to 0. And you have xk, you're keeping going because f of x is not 0. Otherwise, you already stopped. You don't need to go to the next step, right? The reason you're looking for the next iterate is that your f of x is not 0 yet. So what's the best case scenario? What's your hope? The best case scenario is you plug in the next iterate, which you are currently working hard to locate. If you got it, if that's what? I'm hoping that to be what? 0, right? Then you're done. So of course, that's the best case scenario. I mean, of course, we can only hope, right? The reality might be different, but we can always hope. We should always hope. So f of the next iterate, if we can get it as close to 0 as possible, then we're done. Right? So that means 0 is equal to, what I'm trying to do is try to motivate the formula, because we're talking about 3 schemes, they all have different formula, and I don't want you to just memorize the formulas. That will be a pain. If you understand the procedure that I'm doing it here, even if you forget about the formulas, you can derive them in 1 second. That's the power here. So we want that guy to be 0 because that's your goal. It's goal-oriented. You want that to be 0. So that, to put it back in that magic formula we just derived, so that's equal to f prime of c. We don't know c. I'm going to use something, right? STH, something to denote it. Something times x k plus 1 minus xk. All right? I'm going proceeding very slowly because, again, we're trying to motivate 3 schemes together. Once you understand this part, we're going to get 3 schemes at once. Okay? So we have this guy. This equality is key. The eventual goal is to find the root, the 0 of f of x. The current step, we're trying to figure out the next iterate. The goal of this is to evaluate x to the k plus 1, right? xk plus 1. Okay, x to k plus 1. So that guy will tell me how to do that. That's the immediate goal. The immediate goal is to try to, you have your current guess, how do you update it to get the next guess, right? Eventually, by proceeding forever, not forever, for some steps, you're going to lead to the 0 of the f of x. The immediate goal is to get to the next step. So that's why you need to change this quantity. So it reads as xk plus 1 is equal to something. Is that clear? Yeah.
So essentially, we have.
So we solve for this thing, and we get that this is xk minus f at the current iterate xk divided by that something. All right? If you don't see how to solve this in 1 step, again, you need to go back and solve it in detail for many steps yourself. Otherwise, it's very hard to keep track. And this is only the second class. But if you spend time, you'll be fine. We're solving for the xk plus 1. So this provides us with a way to how to go from xk to xk plus 1. Well, assuming we know what that something is. Of course, we don't. The only remaining question is, what is that something? Right? What is that something? So the next is we should define, or actually just approximate, that something. Of course, we cannot just approximate by anything, right? You have to be meaningful approximation. And you should remember what that something represents. The something represents that f prime c, right? The something is this f prime c, remember? And the c is between xk and xk plus 1. F prime c is a slope, right? Is tangent line, is a slope of the tangent line somewhere there, right? The way we define it and we approximate it give us the three schemes. Number one is the so-called chord, which is we take something equals fb minus fa divided by, if you want to finish it, what would you do? B minus A, exactly. That's just because you understand what it means. It's a slope, right? It's a slope. B minus A. And the so-called secant that I wrote down in the title, the secant method is I'm going to take that something equals because again, that's f prime c. For c between xk and xk plus 1 is some sort of slope at a point that's close by. As close by. So the proponent for this scheme says, well, why not just use the previous two iterates? Not only do we have xk, you also have xk minus 1. So if I use fxk minus fxk minus 1, then I should divide by xk minus xk minus 1. Always in terms of a slope. A derivative is like a slope. The last method, which is widely used, the Newton's method, is I'm taking something to be equal to is f prime c. C, I don't know what well that c is, but I know c is between xk and xk plus 1. Right? I don't know xk plus 1. That's something we're looking for, but we don't know xk. Why not just approximate c by xk? That's it. So now we actually use a derivative, not a slope, a quotient as the other two. So take that something to be f prime at xk. There you go. We have three schemes. You plug that something into this equation. Then you're done. You're done. Right? What does that mean? That means chord is that you initial guess. You give me an initial guess x0. right? You make an initial guess. Can be anywhere between the A and the B, and then and let x k plus 1 is equal to x k minus f x k divided by that something, right? So I flip the something, I got b minus a over fb minus fa times f x k. Right, okay. If I just throw this formula at you, you have no idea what it means, and there's pretty much no way you can memorize it without making any mistake. There's a reason, right? There's a reason. Do you understand it? Think of that picture. Think of in one step, you're very greedy. We're all very greedy. In one step, we're done. You get your fxk plus 1 equals 0. That's the greediest scheme, right? Then you're done. Then you're done. You have the formula. Secant. So above the k can be 0, 1, 2, and so on and so forth, right? For the secant, what we have is we're going to get our xk plus 1 is equal to xk minus f xk minus xk minus 1 divided by f xk minus f sk minus 1 times that f xk. Do you see any problem here? So we have the initial guess x0, right? And use another scheme, for example, chord, to obtain x1. Then you can use this. Here the k goes from 1 to 2, 3, and so on and so forth. You get x2, x3, x4. For Newton, we have xk plus 1 is equal to xk minus f xk divided by f prime xk, right? That something is f prime xk. Here the k is 0, 1, 2, and so on and so forth, right? So on and so forth. If there's no more questions, then I'm going to proceed to the next topic, which is to answer the question, how fast? Which is a typical question, right? We're using iterative scheme. How many steps do I need to go? Right? How many steps do I need to go? Is it 17 or is it 1700? That's very different, right? How fast are these schemes converging to the exact solution, alpha? For this period, we're using alpha to denote the exact solution, right? Alpha is a solution to f of x equals 0. So it means you plug in alpha, you get 0. So there's a quantity. The tool here to study is the convergence order. This is another tricky concept, right? It's a tricky concept. Convergence order P. So to write down mathematically, slightly more rigorous is the following. Then I'm going to explain the intuition, right? If there exists a constant C, right, which is a positive constant C. All right, C, such that I'm going to write it like the following. The difference, because you're trying to converge to your exact solution. So what you care is about the arrow. The arrow is xk plus 1 minus alpha absolute value. Right? This is how far you are away from alpha. Right? If the next arrow, right, the next step, the arrow you make at the next step, is less than c times the current step arrow to some power p. P is the order. For all k larger than k0, there exists constant, there exists oops. Oh no. There exists constants k0 and c, right? There's some k0. K0 is a step number. I'm going to explain what this means intuitively, right? So the definition says, if you can find k0, which is a step number, the iterate number k, maybe 100. You keep going after the 100th step. For any iterate after that, the next arrow is no more than a constant. When we say constant in mathematics, in definitions, it just means this has nothing to do with this independent of your k. Because you can argue with me from the preliminary, from the basic math, you can always divide this side by that side, you get a constant c. Then just that c is changing. You have to have your k, have your xk plus 1, then you compute your c. No, that's not what we meant. We meant is there is a c a priori. Like c maybe is 99, something you just don't know. C is independent of your k. If there exists such a c. So what this says is that in plain language, right? Intuitively, the intuition is that my next arrow, xk plus 1 minus alpha, is about the size of xk minus alpha to the p. So they're about the same size. It's no larger than that guy. They're about the same size. Think about this, right? Think about this. What do we, for example, if p is 2, that means after a while, after you proceed according to the scheme, right? After a while, after step k0, your arrow squares each time. So maybe k0 is 99, right? Then your x 101 minus alpha, and you have your 100 minus alpha. Then the next guy is x 101 minus alpha. This guy is 10 to the negative 6. My next guy is what? Is roughly, right, is of the size. When we talk about the size, it can be 9 times that, or at that level. So if k is 2, according to our definition, if the scheme happens to have order 2, p is 2, and xk plus 1 minus alpha is about the size of xk minus alpha to the p's power, p is 2. So the next iterate, the error is about the current error squared. If that's the case, I want you to feel the power of this, right? Then the x 100 minus alpha is about 10 to the negative 6, let's say. According to that, the x 101 minus alpha would be 10 to the what? Negative 12, exactly. So this is about 10 to the negative 12. In one step, you square your error. Right? So you using Marco's example, let's say your alpha is 4, right? Your alpha is 4. Maybe, your x7 is 3.99. 3.99. Okay? Your x8, so x7, the error is 0.01. All right? 0.01. If you know in theory, the order is 2. So we know the next time the error is over here, the error is 10 to the negative 2. The next guy should have error 10 to the negative what? Four, right? 10 to the negative 2 squared. So this guy maybe is like 4.001. So here, the error is about 0.01. Here, the error is about 0.0001. Which is 0.01 squared. If, right, again, there's a big if the scheme has order 2, right? So that's the definition of the convergence order. What we're going to do next on Thursday is we're going to derive the convergence order of secant.